This video lecture is about the structure of our home galaxy, the Milky Way.
The Milky Way band you see on a dark sky far from the city lights is just a small part of the whole galaxy because the dust in the interstellar medium blocks our view of most of the galaxy in the visible band and shorter wavelengths. We need to use longer wavelengths of light such as infrared, and even better, radio, which are not blocked by the dust to map the galaxy. I explained in the previous lecture how we use the 21 centimeter line radiation to map the galaxy. The Milky Way is millions of times larger than the solar system. If Pluto's orbit were shrunk down to the size of a quarter, the nearest star system would be 84 meters away, and the Milky Way would be the size of the western United States. Next slide. We can get an idea of what our galaxy looks like by looking up or down out of the disk plane, where we are able to see other galaxies. The Andromeda Galaxy is the closest large galaxy to us at about 2.5 million light-years away. It is about the same size as the Milky Way. From our vantage point in the Milky Way, we see the Andromeda Galaxy tipped at an angle to our line of sight. The dust lanes outline the spiral arms. Next slide. The galaxy NGC 891 is what the Milky Way probably looks like from a side view. This galaxy has the same ratio of disk to central bulge and disk thickness as our home galaxy. Here's a schematic of the four parts of the Milky Way. The thin disk is where stars are now forming, and most of the light comes from the rare O and B stars, giving it a bluer color, even though most of the stars are fainter K and M stars. Confined in an even thinner band is the interstellar dust layer, and X marks the spot where our solar system is. At the center is the bulge composed of old stars made of heavily processed gas, so the gas is from numerous previous generations of stars. Such gas is what astronomers call metal-rich, where the word metal here means atoms heavier than helium. Merging smoothly into the bulge is a stellar halo composed of old stars made of primordial or only slightly processed gas. Such gas is called metal poor. The stellar halo stars have very elliptical orbits tilted every which way, so they plunge in and out of the disk and bulge like a swarm of bees. Permeating through all of the visible parts and extending even farther out is the dark matter halo. Dark matter is material that does not emit or block any kind of light, but has a significant gravitational effect. I'll talk a bit later how we know it's there. Terrestrial planets are able to form only in galaxies because the gravity of a galaxy, especially one as massive as the Milky Way, acts like a container keeping the heavy atoms blasted out by supernovae inside the galaxy. So the previous generations of stars can increase the metallicity of the interstellar gas clouds over long periods of time. The Milky Way is much older than our solar system, so it has been able to form a few 100 billion stars. You can estimate the total number of stars by dividing the total mass of the galaxy by the mass of a typical star to get the rough order of magnitude estimate shown here. I'll talk about how we find the galaxy's mass later in this lecture. Globular clusters get their name because they look like a glob of hundreds of thousands to a few million old stars, all bound together by their mutual gravity. Most of the 150 or so globular clusters in the Milky Way are part of the stellar halo and orbit around the center of the galaxy in very tilted elliptical orbits. The fact that the distribution of globular clusters is concentrated in the direction of the Sagittarius constellation, instead of being sprinkled randomly all over the sky, tells us that we are not at the center of the galaxy. If we have a way of measuring the distances to all the globular clusters, we could determine how far out from the center we are. We now know that we're about 27,000 light-years from the center. Next slide. Some stars are very useful for finding distances to star clusters and to other galaxies because they have a known luminosity that is large, so they can be seen from great distances away. One very important type of star for finding distances to star clusters and galaxies is called a Cepheid variable star. A Cepheid variable changes its brightness by changing its size and temperature with a pulsation period that depends on its average luminosity. More luminous Cepheids take a longer time to expand and contract. They have a well-defined relationship between their average luminosity and pulsation period, as shown in this graph. Because the luminosity of Cepheids can be easily found from the pulsation period, they are very useful in finding distances to the galaxies, or clusters, in which they reside. Once we find the stars that are pulsating, we measure their pulsation period and their apparent brightness, and then use the period-luminosity relation to get their luminosity, and then find their distance from the inverse square law. We figure out how far away the star needs to be to appear as dim as it is in our sky. Cepheids are so important that being able to measure their distances in other galaxies was the main factor in determining the size of the Hubble Space Telescope mirror. That is, how large did the mirror need to be to have the resolving power and light gathering power to pick out individual Cepheids in other galaxies? The Cepheid distance measurements of 18 galaxies was one of the 3 key projects for the Hubble Space Telescope during its first decade of operation. All of the pretty pictures of other objects during that time were just an extra bonus. Next slide. To find the masses of planets, we look at the motions of satellites orbiting them. To find the masses of stars, we look at motions of stars orbiting each other. For the Milky Way, we use the orbital motions of the stars or gas in the disk to find the total amount of mass enclosed inside their orbits. If you know the orbital speed and the orbit size, you can find how much gravity force it takes to accelerate the star or gas cloud. That gives us the enclosed mass inside the orbit. When you do this for different orbit sizes, you find how the mass is distributed in the galaxy. The rotation curve is the plot of orbital speed along the y-axis versus the orbit size, distance from the galaxy center, along the x-axis. The rotation part of the term refers to the motion of the disk as a whole. As a whole, the disk seems to be rotating, spinning, even though it is really the individual stars and clouds that are orbiting around the center. The rotation curve tells you the amount of mass inside a given distance from the center. The higher the orbit speed, the greater is the amount of the enclosed mass. You find how the mass is distributed in the galaxy by looking at how the amount of enclosed mass changes with the size of the orbits. Next slide. The rotation curve for the galaxy stays pretty flat out to great distances instead of falling off. The flat rotation curve that is significantly higher than expected from the gravity of the stuff we can see, the visible matter, shows us that there is a lot of material that is not visible. The higher the orbit speed, the greater is the amount of the enclosed mass. The gravity of the visible matter is too weak to accelerate the stars and gas as much as we see. Next slide. The extra gravity is supplied by material that emits and blocks no light. That strange material is called dark matter. The dark matter is not made of ordinary atoms. It is probably made of some kind of exotic particles predicted by quantum mechanics that we've been trying to detect in our high-energy particle accelerators without success so far. You can think of the Milky Way as a big blob of dark matter with a shiny component of stars, gas, and dust in the center of it. From the fact that the rotation curve stays fairly flat out to great distances means the dark matter halo extends out much farther than the visible disk and stellar halo. Next slide. This slide is a repeat of one I showed in the interstellar medium lecture about how we use the 21 centimeter line radiation produced by neutral atomic hydrogen gas to map the galaxy. Things closer to the galaxy center are able to move by greater angular amounts than those things farther out, so we get different Doppler shifts of the hydrogen gas. The brightness of the emission depends on the amount of hydrogen gas, and the Doppler shift gives us the velocity. We observe the 21 centimeter emission along narrow beams and systematically build up a map of the galaxy. The velocity, from the Doppler shift, of each clump of gas along a given strip corresponds to a particular distance from the center of the galaxy. Gas clump by gas clump and strip by strip we create a map of the galaxy. I have another link to the H1 4Pi survey, which took several years to compile. At the bottom of the slide is a nice, scientifically accurate painting of the Milky Way released by NASA in 2008, with the sun's position in the Orion spur of one of the spiral arms indicated.